If you recall yesterday, we integrated a vector field over two different paths, and those two different paths had the same starting and ending point, and we ended up with the same result, -36 in both cases. I claimed, without supporting evidence, I mean, we've got two, I guess, but without supporting evidence that this will happen for any path between our starting point and ending point. If you integrate this vector field, starting at 3, 0 and ending at 0, 3, no matter what, you'll always get -36. I didn't verify that, but we'll just go with proof by persuasion. Then we wondered, is this going to be true for all vector fields? And the answer was no, this is not going to be true for all vector fields. So that raises the question, what kind of vector fields have this property? What we want to observe about this vector field is that this vector field is a gradient field. I didn't tell you that at the beginning. That would have given this part away. So we got the same result because f is a gradient field. That is, f is the gradient of f for some potential function little f. So two vocabulary terms in rapid succession: gradient field, potential function. So we're saying that f at xy is the gradient of some potential function f. That is, we'll have some fx at xy times I and fy at xy times j. So let's try to find this potential function. What is f the gradient of? Let's find it. Let's find a potential function for this gradient field. What that means is that this gradient field is fx at xy times I plus fy at xy times j. And we know what the two components are. So this is going to be 3 plus 2xyi plus x squared minus 3y squared j. So I'm looking at the two first partial derivatives of our potential function. So if fx at xy is 3 plus 2xy, I should be able to integrate this with respect to x to find our, at least part of our potential function. So let's integrate that. So the integral of 3 with respect to x is 3x. The integral of 2x with respect to x is x squared. But there's a third thing. Normally when we integrate, we write plus c, but remember, this is a partial derivative that we took with respect to x. So not only will we have to think about a constant that could show up as a constant of integration, but we could have an entire function of y that the derivative with respect to x considers to be constant. The partial with respect to x will treat a function of y as a constant. When we take the partial derivative with respect to x, we will treat any function of y as a constant. So this is the information that we get from the partial derivative with respect to x. Let's go over to the partial derivative with respect to y. Leave a space, and I'm going to put it down here and go up. So the derivative, the partial with respect to y is x squared minus 3y squared. So let's integrate with respect to y. So f at xy, the integral of x squared with respect to y is x squared times y. The integral of negative 3y squared with respect to y will be minus y cubed. But here we have the derivative. This was integrating with respect to y. The partial derivative with respect to y will treat any function of x as constant. So there might be some function of x So the same line of thinking. We integrate with respect to y. We're not just going to write plus c. We're going to write plus some function of x. But for the same reason that we write plus c when we're integrating. Now we look at our two potential functions. And we see they have a term in common, x squared y. That one matches up. Notice that our potential function, when we integrated with respect to x, gave us a 3x. That must be the function of x that the partial derivative with respect to y treated as constant. Notice that when we integrate with respect to y, we have this term minus y cubed that we didn't have when we integrated with respect to x. That must be the function of y that the partial derivative with respect to x treated as constant. So if we gather all these things together, our potential function could be what they have in common, x squared y plus 3x, that's our function of x, minus y cubed. I suppose we could have some constant out here too. So here's a potential function for our gradient field. Take the partial derivative of this function with respect to x, we get 2xy plus 3, and then the rest is 0. And that is 3 plus 2xy, our I component. If we take the derivative of this function with respect to y, we end up with x squared 0 minus 3y squared, which is our j component of the vector field. So this is a potential function for our vector field. Any questions? How's everybody okay? So when we're looking at this vector field, the vector field that we're integrating, we're saying it's the gradient of this potential function. And we got this potential function by integrating. It's like the gradient field is some kind of derivative of the potential function. Let's see why we care. Oops, it's that page. Way back in the second week when I wrecked this page. And this page when I realized I wasn't using the right pen. Gradient of f means the gradient of the function. So here's where we're going to start making a connection to something from our past. Think back to the fundamental theorem of calculus. The fundamental theorem of calculus says if you want to integrate a derivative, just evaluate the function at the endpoints. Integrate a derivative, evaluate a function at the endpoints. Integrate the derivative, just evaluate the function at the endpoints. Don't worry about what's going on in the middle. Find the antiderivative, evaluate at the endpoints. And we just had an example where we were integrating and the start and the end were the same point. And then we said the vector field was a gradient of some potential function. And the gradient is built on derivatives. So we're going to upgrade our fundamental theorem of calculus to apply to line integrals. So I'm writing my generic line integral, the integral over C of the gradient of f. So remember, the gradient of f is a vector field. So it makes sense to write dot dr, the same line integral that we've been working with. So if you integrate a gradient of a potential function over some curve, and C is any path from point P to point Q. We can do the same thing that we did with the fundamental theorem of calculus. Evaluate the potential function at the endpoints. So what that means is that if we had known this before we did the example yesterday and identified our vector field as a gradient field, we could have just found the potential function like we did, and then evaluated that potential function at the two endpoints. It would have been a lot less fun because we wouldn't have had to parameterize any curves. We wouldn't have been able to calculate that dot product. We would have missed out on a lot. So what we notice is that the vector field from yesterday is a gradient field, and we can just evaluate the potential function at the endpoints. So we notice that F is a gradient field. Which means that we could just take F and evaluate at the endpoints. Already forgotten what F is. Criticism for me of me by some of my colleagues. Leach has forgotten what F is. It's like I need to flunk more students or something. Let's find out. Hopefully we've done some calculations correct. This is supposed to come out to -36. Let's plug 0, 3 into this function, and then plug 3, 0 into the function, then subtract and see if we get the same thing that we did yesterday. So I'm going to have x is 0, y is 3. This is really going to mess with me right now. X is 0, y is 3. That's what we're plugging in first. So 0 squared times 3 plus 3 times 0 minus 3 cubed. So that's plugging in 0, 3. Now I got to plug in 3 zeros. So I've got to switch those two. This is not going to go well. historically. X is 3, y is 0. So 3 squared times 0 plus 3 times 3 minus 0 cubed. Zero, 3, 3, 0. Take a drink of coffee. That was hard. Even with all these zeros running around. So from this first term, we get negative 27. And from the second term, we get 9. Just like we suspected. If only we had known the fundamental theorem of calculus for line integrals and noticed that our vector field was a gradient field. We describe gradient fields as path independent. Because when we integrate them, it doesn't matter what path we take. We just need to care about the starting point and the ending point. Another word for path independent is conservative. Right now, the better descriptor is to say path independent, because that's just what we're basing this on. Path don't matter, starting and ending point matters. It's not the journey, it's the destination. Not all vector fields are gradient fields. Not all vector fields are path independent. So that's when we would have, if we wanted to find a line integral, if we notice that our vector field is not a gradient field, it is not path independent, then we will have to go through all of the work like normal. Not all vector fields are path independent. Not all vector fields are gradient. So the fundamental theorem of calculus for line integrals only applies to path independent fields or gradient. And it's like the vector calculus version of the fundamental theorem of calculus. That's why it's the fundamental theorem of calculus again, this time for line integrals. If you're thinking, man, there seems to be a lot to this fundamental theorem of calculus business. We had two parts to the fundamental theorem of calculus when we just had functions of one variable. And now we've got this new fundamental theorem of calculus that applies to line integrals. So you might be thinking, how many fundamental theorems of calculus are there? There are two more. After this, there are two more. So in vector calculus, we have 3 fundamental theorems. That's a lot of math for an engineering class. Any questions? Comments? Snide remark? How's everybody okay? Everybody looks so burnt out. But I might be projecting. I don't know. You kind of all look the same as you did like in the second week of class. Maybe I'm just projecting my burnout onto you and I'm reading it as burnout. You know what I mean? It's like the assessments you make of other people say more about you than they do about other people. You got a professor saying, man, you guys all look burned out. That's probably because the professor is burnt out. Because for the most part, like all semester, y'all have just been kind of staring blankly at it. It's kind of like stunned. I've been trying to summarize this in 5th edition Dungeons and Dragons terms. And it's better than the monk ability because the monk has a stunning strike, but everybody gets a con save versus that. But then again, a monk can do that as like part of their attack. So as part of their action or their bonus action. I can stun an entire room full of people, but there's a pretty significant casting time. I mean, I have to talk about math. There's a pretty significant verbal component to this spell. So it's like casting time, 15 minutes. That doesn't make any sense. In D&D 5th edition, there wouldn't be a casting time of 15 minutes. It's either going to be 1 action, 1 minute, 10 minutes, or an hour. There's no in between. It has to be one of those. You know what I mean? Like if you're doing like homebrew stuff, don't make the casting time 15 minutes. Make it 10 minutes if you want it to be that long. You know what I mean? Also, if something can be done at a distance, 30 feet, 60 feet, 90 feet, 120, or 150. Got to be multiples of 30. I don't know why. That's part of the design. So if you make homebrew, and it's like, oh, range 40 feet. I don't know. You're just going against all the tradition. I make all my ranges multiples of 20 feet. I'm not like one of those Brittany and Justin wannabe homebrew. Anyway, what I'm saying is I can stun an entire room of people, but it takes me 10 minutes and I have to talk about math the whole time. And it's not a con save. It's an int save. So if you're like, oh, no, I totally get what's going on. I am not stunned. That just means you succeeded on your int save. You know what I mean? Game terms. Any questions? Comments? Smart remark? This is the big deal for today, the fundamental theorem of calculus for line integrals. I want you to see how closely it matches the fundamental theorem of calculus, where you integrate a derivative by evaluating the function at the endpoints. You integrate the gradients by evaluating the function at the endpoints. That is pretty dope. That's going to do it for today. I'll see you all on tomorrow. We'll talk more about how to determine by looking at a vector field if it is in fact a gradient field. That's it for today. I'll see you all on tomorrow. Everybody have a good day and thanks for playing.